Hello, cool. Right, so this is for second years. We're going through the A questions for oscillations, and we'll start naturally with A1. I hope you can see all this. Let's get cracking. So A1, is that big enough? Yeah, that'll be fine. A1 asks you about a system where you've got this equation here, and we're just asking a few warm-up questions to this. Now, the first question is write down a general solution to this differential. Hopefully by now it should be taken as read that you've got a simple harmonic here, and any solution, if you're asked for a solution to a simple harmonic, you should go for a wave equation. Now, in my case, I went for the general solution is y equals c, have an amplitude in there, and then you have your wave, which is cos, times by this omega t plus a phase difference here. Now we don't have to do this for the question, that's the answer, but we'll just have a little step through to show that that makes sense. So let's do this differential with respect to time twice. So let's do y dotted once. So we get c, that comes out the front. Now the differential of cos, of course, is minus sine. So we can times it by minus sine omega t plus the phase difference here. Now, of course, we've got to remember, because we're differentiating with respect to time, we have to differentiate this term as well and drag it out of the trigonometric function. So when we differentiate omega t, we just get omega. So we can times by omega there. So now we get we get omega c sine omega t plus the phase difference, and that is all negative because, of course, sine is negative when you differentiate cos. Right, let's do that again. So, same basic principle. When we differentiate sine, we get cos. There's no need for a sign change. Of course, that's a sine with a g. So there is a sign change, but there's not a sign change. So we keep the negative sign here. We put wc. Those are all, none of those have anything to do with t, so we keep them the same. Sine changes to cos. We get omega t plus the phase difference, and of course we times by that omega again, because we're differentiating what's inside the trigonometric function. So in short, that gives us minus omega squared c cos omega t plus the phase difference. Hopefully you'll see now that this is in fact our original y, which is good news, because then the double derivative with respect to time of y is just minus omega squared y. Let's pop that back into the original equation. We get minus omega squared y plus omega squared y equals 0, which hopefully will need no proof. We can take that as read. Smashing. So yeah, there's our general solution to part A. Now, part 2, it asks us, write down a solution to the differential equation that satisfies the initial conditions, y equals y naught. So let's get our equation down. So this is the one from just part 1. Yep, that's all good. So let's get our initial equations down, which is y naught, smashing, and dy over dt equals 0, and this is all at time t is naught. So the first one, probably the easiest thing to do here in this case, is say that we write out our equation and then we just make t 0. Okay, which is nice and easy. So we have y equals c cos 0 plus the phase difference. So we have just c cos phase difference here, and we know that this equals y naught. So we'll just make that equal y naught. So we already have an equation for y naught, which is lovely. Now let's put our dy over dt in. So let's differentiate this bad boy again. C cos omega t plus the phase difference. Did this last time, shouldn't be too much of an issue. Ooh, there we go, not going off the page. It's minus omega c sine omega t plus the phase difference. Now this equals 0 as well. Apparently at time t is 0, which is all good. So let's make t equal 0. So that equals 0 when t equals 0. So therefore we have minus omega c sine phase difference equals 0. Okay, smashing. Now, of course, these guys we can kind of divide by and they just disappear. Because 0 divided by them is still 0. And we ask ourselves, sine of a phase difference equals 0. What is that phase difference going to be? The answer is, I believe it's something along these lines of 2 pi n, where n is any integer. But I don't think that's what they're really looking for here. I think they're just looking for the simplest case, where the phase difference here actually equals 0. So that's nice and simple. So we know that this is one solution thereafter, and then the second one is back up here. We're looking for this c cos phase difference equals y naught. Actually putting this solution to the phase difference back in up here, we can get c cos 0 equals y naught, and cos 0, as we all know, is just 1, so that goes to y naught equals c. Let's pop those back in to our original equation we wrote up the top there, and we get y equals y naught cos omega t plus 0, so let's leave that out. And there's your answer to part 2. Lovely. Okay, so those two should have been pretty introductory. Hopefully no troubles there. If not, don't worry at all. Take your time with them. So now, let's go on to part 3.